Hello, I've spoken about planets and the moon and the asteroid belt. So next stop in this tour of the solar system is comets. And these hit the news every so often because you get spectacular images like this one here. I mean, this is Comet Hale-Bopp, which came past in 1997. It was a particularly bright comet. You could see it with a naked eye just about. And it was easily visible. If you had small telescope or binoculars or something like that, you could easily see this for well over a year. This is one of the most prominent comets that we've had in quite a long time. And people are familiar with what comets look like. I mean, everyone's seen these sort of images where you've got a bright nucleus, you've got a tail coming off the back, or in this case, we've got two tails, which I'll come back to later on. People have seen these sort of things many, many times. They've heard of Halley's Comet, if nothing else. A lot of people will remember that from 1986, the last time it came past and caused great excitement on the news. And I mean, we see Halley's Comet in our history lessons when we're doing the Norman Conquest, looking at William the Conqueror, 1066, Battle of Hastings, all that sort of thing. Halley's Comet is included on the Bayeux Tapestry. So comets are really, really in the public consciousness. But it leaves us a lot of questions. Why do they look like this? Where do they come from? Why do they take so long to come back again, if indeed they do come back? I mean, Halley's Comet, as I say, it came past in 1986. It's going to be back again in 2061. So why are we waiting 75 or 76 years for it to return? And that's relatively quickly for a comet to come back. I mean, this one here, Hale-Bopp, you're looking at 2,500 years until it is predicted to return. So we certainly won't be seeing that for a second time. So what is going on with all of this? Right, well, let's first of all think back to what I was saying in the asteroid belt video. And I spoke about the Kuiper belt and the Oort cloud. So these are two other locations in the solar system where you get a lot of objects that aren't planets. So they're a long way away from the sun, much further away than the asteroid belt. Remember, the asteroid belt is between Mars and Jupiter. You're looking at maybe 3 times the distance from the Earth to the sun to the asteroid belt. So 3 astronomical units, give or take. The Kuiper belt, Oort cloud, much further away. The Kuiper belt is beyond the orbit of Neptune, and the Oort cloud is even further away from that than that. So let's get a idea of the scale of this. So 1 astronomical unit, that is Sun to the Earth. 30 astronomical units, that's Sun to Neptune. Kuiper belt is then beyond that. So we're looking, we might be 50 astronomical units or something like that away from the Sun. This is a long way away. And inside the Kuiper belt, you've got lots of objects. You've got asteroids, you've got dwarf planets like Pluto, and then you've got comets or potential comets, and things like Halley's Comet originated in the Kuiper belt. So what do I mean by potential comet? Well, comets are often referred to as dirty snowballs, and you get objects in the Kuiper belt which are exactly this. They are a lump of rock, irregularly shaped rock, and they will have ice with dust all over the surface of this rock and into holes inside the rock and all the rest of it. So by ice, I mean in water ice, as well as frozen carbon dioxide, carbon monoxide, methane, ammonia. All of these things, we're a long way away from the sun here. It's cold, all this stuff freezes. And they freeze with dust inside them, and that all then sticks to this rock. So you get this really dirty black mixture of rock with ice and dust stuck all over the top of it. And by and large, these are just orbiting around quite happily around the sun, all outside the orbit of Neptune, and no one really gives them much thought. Occasionally they get disturbed in their orbit, and then they head towards the sun. And some of them can fall into stable orbits. Some of them won't fall into stable orbits. So you'll get some comets they'll head off towards the sun and they'll just pass by and they won't come back. They're in what's known as a hyperbolic orbit. So you'll have the sun, they'll come shooting in, they'll do a really close approach, and then they'll just shoot off, never to be seen again. Some of them, like Halley's Comet, will fall into stable but highly elliptical orbits. So if we've got the sun over here, we've got the Oort cloud, Kuiper belt over here, or it could be the Oort cloud for ones that are much, much further away, but let's stick with the short period comets at the moment and the Kuiper belt. So they're going to head off on these really elliptical orbits. Now remember, Kepler's first law is saying anything that's in a stable orbit around the sun is orbiting in an ellipse. And it's no different for the Earth. If the Earth is here going around the sun, it's moving in an ellipse, but not with high eccentricity. The orbit of the Earth, compared to a comet, certainly, is pretty much circular. Comets, nowhere near circular. They have highly eccentric orbits. And this is why it takes so long for them to come back. They got to travel a long way. Getting all the way around this orbit takes ages because it's a long orbit. And also, Kepler's second law, the comet is moving a lot faster when it's near the sun than it is when it's far away. Remember, it's got to sweep out equal areas in equal time as it's moving through its orbit. So, an area around here, that amount of time to cover that bit of orbit is not sweeping out a big area. So it's moving a lot slower when we're further away. So that means it takes even longer to come back. So that's why we're getting these 76-year, periods on the orbits of things like Halley's Comet. The other thing that's happening, of course, is it's moving along this orbit. It gets closer and closer to the sun. Well, it's going to heat up, and the dirty snowball is going to start to melt. These dirty snowballs have got very low albedo. Remember, we spoke about albedo in the video on the moon. And albedo, that's meant to be one word. I don't know, I've got a big gap in there. Albedo. That's how much light it reflects. And comets don't reflect much light. They're dirty, they're dark. They absorb a lot of light, which means they're absorbing a lot of energy, and then they start melting. So the ice starts melting, and then that gets released as gas, and the dust that is in the ice then gets released as well. So you're getting gas and dust coming out of the dirty snowball. So we start off with something that is frozen, then it starts to melt. So we've got our nucleus with then gas and dust in what's referred to as a coma around the nucleus. Coma comes from the Latin for hair. So this is like a sort of covering around the nucleus. Then the solar wind and the radiation from the sun, so all of these photons and all these charged particles that are being pushed away from the sun in the solar wind, then push away the coma into tails. And we get two tails. We get one of gas, which is this one here on the left. This is our gas tail, the blue one here, the fainter one. And then we've got the one on the right, the brighter white one, which is a tail of dust. Now, why are there two tails? Right, let's draw a sketch of this, because this is one of the common misconceptions about comets. People look at a comet, say we had a comet with just one tail on it. So we've got our nucleus and we've got a tail coming off the back. If you ask someone what direction is the comet moving in, most people will say, yeah, it's moving that way, which is why the tail is coming out the back. Yeah, this is what we're used to on Earth. If you move forwards, anything that's going to be going out the back of the object and getting left behind will be directly opposed. It'll be in the opposite direction to the motion. Not so for comets, and this is why we're getting two tails. So we've got here our central bright bit. We've got a gas tail, which is going off that way, and then we've got a dust tail. So I'm going to draw in, which has got a slight sort of curve to it. You can see it's sort of coming off. You've got a bright bit here, and then if you follow the bright bit round, it's on a bit of a curve. Okay, I've slightly exaggerated it there. But the gas trail, you can see, is fairly straight lines coming off here. There's a bit of a curve in the dust tail. So it's sort of curving off that way. Now, the reason we've got these two with a bit of curve in the dust, the gas tail is directly away from the sun. So it's getting pushed, the gas particles are much lighter. We've got things like carbon dioxide, carbon monoxide, methane. None of these things are particularly heavy. They're getting pushed away. So they go directly away from the sun. So if we take our gas trail, it will immediately tell us where the sun is. So the sun is over here. Now, the dust tail is also initially being pushed directly away from the sun, but with the heavier particles, it is encountering a bit of friction. Whether it's with the the solar wind, any other particles that might be around, it's slowing. So it's got a bit of a drag factor on it with the dust tail. So it gets pulled away, it's getting pushed away from where the sun is, so it's getting pushed in that direction, but it's also getting dragged in the opposite motion to the comet. So it's getting dragged off this way, which is telling us that the comet is actually moving that way. So on this particular image, the direction of the comet is this way. We know that the comet isn't moving directly towards the sun. If you've got the sun there, even on these elliptical orbits, they're coming in, they're doing that sort of motion. So if you're at a particular point on the orbit, let's say we were here. So say we're here, the comet's going to be moving around that way. So you're going to get the gas tail is going to be directly away from the sun, and then the dust tail is going to be sort of curving away that way. So, and the direction of motion is that way. So the tail isn't necessarily directly out the back of the comet. You're going to get a more extreme case when you're here, when we're in this point of the orbit. So the gas tail is going to be going that way. The dust tail is going to be going sort of that way. So it's going to look like that, but the direction of motion is going to be down here. Pretty much perpendicular to the gas tail. So don't fall into the trap of thinking that it's just that's how you determine what direction the comet is moving in. So this is why we're getting two tails, essentially, because of all of that. So that's covered where they've come from, the comets. In this case, for a short period, the Kuiper Belt, long period, Oort cloud. Why they look like they do, what they're made of. They are connected to other events in the solar system, and that's meteor showers. They're leaving behind all of this gubbins, and they're cutting across the orbits of all of the planets. They're coming from way out, and they're coming in really close to the sun, so they're cutting across every orbit. So as we then pass through the debris that is left behind by these comets, we're then going to get all of this debris is going to be coming into the atmosphere of the Earth, and that is going to cause meteor showers. So we're essentially passing through the leftover tail of a comet, all the stuff that's been left behind. So the Orionids, which are quite prominent in October, that is actually the Earth passing through what's left behind from Halley's Comet. I mean, they're called Orionids as a meteor shower because they appear to be coming from the constellation of Orion. That's why we're seeing them in October, Orion being an autumn-winter constellation. So as the Earth passes through the remnants of the tail of Halley's Comet, we get meteors. Another one, Perseids. The Perseid shower, which is a summer one, that's in August. And that is passing through the leftovers of Comet Swift-Tuttle. Now, not all meteor showers are the result of comet debris. Some of them are from the breakup of asteroids, but a lot of them are connected to comets. So, we get an added bonus. Not only do we get to see the spectacular sight of looking at a comet when it comes past, but they give us more spectacular sights by allowing us to look at meteor showers as well at various times in the year. So there you go. That's a whistle-stop run through of comets. Hopefully to clear up a few things on that.